Mr. True. In this video, I want to talk about the relationship of a two-dimensional object and how it changes when you change the lengths of the side of a two-dimensional figure. Now, most of this video is going to be focused on perimeter and area of similar figures, but building up to the idea of similar figures, let me actually go out of order a little bit and talk about my first example here. When you have a two-dimensional figure, and I've picked a very simple one, a square, and you change its dimension. In this case, I'm going to take this 1 by 1 square, I'm going to make it 4 times as long. Well, I've got my drawing here, and you can see that if I increase the length of this square to change it into a rectangle, if I increase the length by a multiple of 4, then what did have an area of 1 by 1 or an area of 1 now has an area, as you can clearly see, of 4. It's gotten 4 times larger. Now, I kind of want to change my notes as I start my video here. Let's summarize what this says. If I only increase the length, which is one dimension, by 4, my area is going to get 4 times larger. Now, this doesn't apply exactly to the 4 examples I'm going to do in a second because these two figures are not similar. But again, I want you to see that I took the length and multiplied it by 4, and the area got 4 times larger. Well, if I take this out, and I not only increase the length by 4, but I increase the width by 2. So now we're going to have, kind of change my notes a little bit on the fly, so my drawing's not going to be quite as neat. But if I increase the width by a multiple of 2, and I increase the length by a multiple of 4, well, the length I multiply by 2, or let's change that back to a 4, if we want to just talk about this way as being length. 1 times 4 is 4. And the width, I increased by a multiple of 2. Well, what did have an area of 1 is now going to have an area of 8. So if you look at two, let's say, sort of like, well, not a box, so I want to say a box because it holds stuff, but an area that's, 1 by 1, area 1, I increase the width by 2, the length by 4. Those multiples on the length and width are going to together change the area. So 2 times wider, 4 times longer, that's a multiple of 8. So the old area can be multiplied by 8 to find the new area. Now, of course, these are rectangles. I know area is length times width, but what if it was a shape that we didn't know the area or could not easily find the area of? Well, how you change the length and width in this two-dimensional figure is how the area is going to change. If I made it 3 times wider and 4 times longer, well, 3 times 4 is 12. So if this had an area of 2, which it doesn't because it's 1 times 1, but if something had an area of 2 and you made it 3 times wider and 4 times longer, that area would be increased by a multiple of 12. So what did have an area of 2 would have an area of 24. And again, I'm kind of going off the cuff here with my notes because I keep saying 2 now and area is 1. But how you change the length and width together change the area in terms of multiples. Now, if you specifically talk about similar figures, I just kind of wanted to expand on that because my textbook just in this section deals with similar figures. Now, if you talk about similar figures, remember similar figures are two figures that have the same shape but may vary in size. Well, if I have if I have a square and I make it 4 times larger and I create another figure that's similar, it's going to, remember when we talked about similar figures, that was the proportion of change for each of the sides had to be equal. So the length and the width, if you will, is going to change by the same multiple. So what we have here is the scale factor, remember that's just something you're multiplying by, the scale factor of two similar figures, same shape, but may vary in size, is A over B. Then the ratio of the perimeters is A over B. Now, let's go back to one way of proving two triangles are similar. One of the theorems that we learned was the side-side-side theorem. Now, that was also a congruency theorem, but when we talked about similar figures, we took the sides and divided the 3 pairs of sides in the same order to see if the ratios were the same for all 3 sides. Lengths. This is a length. maybe of just one corresponding pair of sides, but it is taking the lengths and dividing them to get some kind of ratio. Well, perimeter is a length as well. It's the length all the way around the object. So it makes sense that the multiple of change for the perimeter is the same as the ratio of change for the two similar figures, or maybe, if we know they're similar, I only have to check this for one pair of the sides. But now again, the area is going to get changed by a squared over b squared. Remember, we're talking about similar figures. The ratio of change in both the two dimensions must be the same, and that's why it's being squared. So it's not like I have an area of 1, I increase the width by 2, the length by 4, so the area gets to be 8 times larger. And yes, I know again this area is 8, but 8 times 1 is also 8. With similar figures, that length and width is changing the same. Thus, you have this squaring idea. So I've got a square with the length of 1 by 1. I've got another square, which is similar because they're two squares. They're two, well, I'm saying they're squares. I guess I should mark little right angles in the corners, but take my word for it. And the length and the width both got changed by a multiple of 4. So the area, if we talk about setting up the large figure over the small one and getting 4 over 1, that's the ratio of this side to this side or this side to this side, then the overall area is going to be 16 times larger. Now, of course, I made this example very simple, of course. This does have an area of 1. This does have an area of 16 by doing length times width. But if this area were, let's say, 2, then this area would be 32, or 2 times 16. Increase length and width, 2 dimensions by a multiple of 4. So the shapes are similar, and the area is 4 squared, or 16 times greater than whatever the smaller area was. If you were going in reverse, I set this ratio up as going as large over small, so I'm kind of like going from small, when I say 16, it's whatever this area is times 16 to get this particular area. If I was going in reverse and I wanted to take the large area and convert it down into the small area, well then I would be dividing by 16, or I would have 1/16. So I got 4 examples, and let's get to them right now. First example, what is the ratio of the perimeters and the ratio of the areas? Now, when you set up ratios, you get to control over how you set them up. So if we read this as going left to right, or if I decide that I want to go, let's say, my small measurements over my large measurements, that is how I'm reading this left to right, then, and these are, I've been told that these two parallelograms, or these two polygons anyway, are similar. They don't have to be parallelograms. I don't have any parallel marks up here. But these two polygons are similar. So I'm going to take the sides that I do know, which is 2 and 5, and if I'm going from small to large, then it's going to be 2/5. And whatever the ratio we have, or the multiple of change, if you will, between the sides, if they're similar figures, then that's also going to be the scale factor, the ratio of change, or the proportion of the perimeters. And then the area is going to be that ratio squared, so it's going to be 4/5. And I don't know why I'm wrapping this in a set of parentheses. So the ratio of change, the proportion of the perimeter is 2/5, just like one pair of sides if they're similar. The area is going to change by a ratio of 4/5. Now that is if we decided to set this up as going from small to large. If I want to read this in the opposite direction, just for argument's sake, and I decided that I wanted to do the large measurements over the small ones, then pick this, pair of sides that you have, corresponding sides that you have in our similar figures, and we're going to have 5/2. So that's a ratio for the perimeters, and the area is going to be that squared. So 5 squared over 2 squared is going to be 25/4. And I'm starting to realize that when I took this 2/5 and I squared it, I squared the numerator but not the denominator, and that is a very common mistake that I see my own students make when they're trying to rush through a test. I'm trying to talk and write at the same time, and sometimes I do it very well, and sometimes I don't. Anyway, so the ratio of changes are 2/5 and 4/25, and or 5/2 and 25/4. Now, you know, which way is right? Well, let's take a look at that over here. They're both technically right. It just depends on what the question is asking for, which way is going to be most convenient. What's the area of the smaller triangle? So I want to take this larger area of 35, and I want to reduce this area of 35 to find the area of this other triangle without attempting to find its height. You know, area of a triangle is 1/2 base times height. So I could say that 35 is equal to 1/2 of the base of 5 times a height of h, and actually solve it for h, and then with understanding of ratios here, kind of work out the height of the smaller triangle. But that's extra work that we don't need to. I got everything I need right here without trying to find the height of the large triangle and reduce it to find a height of the smaller triangle. I got everything I need to find the area right now. Just got to take one little step. Now, the ratio for the sides, which is equal to the ratio of the perimeters, as we saw over here, again, they're similar. So do I want to set the ratio up for the sides as 3/5 or 5/3? Well, clearly this area of the smaller triangle is going to be less than 35. It's a smaller triangle. So do I want to multiply by a ratio that's smaller than 1, or do I want to multiply by a ratio that's greater than 1? If I multiply by a ratio, 5 divided by 3 is 1.6 repeating, or 1 2/3. If I multiply by a number that's greater than 1, then I'm kind of pausing because I'm thinking, well, you know, I could say greater than 1 and less than -1, but with areas, I can ignore those negatives there. If I multiply by a value greater than 1, then I'm going to get a larger answer, but I know my area is going to be smaller, right? So I want to multiply by a ratio that's less than 1. So I want to do 3/5. I want to do 3/5 as my ratio for either the perimeters or the sides, my ratio of change that I have between these two similar figures. That means, so this is going to be more convenient. They're both right, but this will be more convenient to convert 35 into a smaller area. So if the ratio of my sides is 3/5, then the ratio of my areas is going to be 3/5 squared. And this time I'll remember to square both the numerator and denominator. Now I'm going to take this, this 35, and I want to find this area, which I don't know, but I'm going to find it by taking this area of 35, multiplying it by 9/25. And yes, I like to give us examples that don't work out exactly even because, well, if I have the chance to teach you something and review some skills with you, I'm going to. 35 and 25 are both divisible by 5. So if I go ahead and put this over 1 and reduce this multiplication before I try and actually do it, because I'm going to attempt to do it in my head, 35 and 25, both of these numbers are divisible by 5. 25 divided by 5 is 5, and 35 divided by 5 is 7. So the area of the smaller triangle is going to be set. Now when you multiply fractions, this is kind of, you know, scratch workish sort of looking, but when you multiply fractions you go straight across the top and the bottom. So 7 times 9 is 63. 1 times 5 is 5. And again, I don't like to teach you in a way that makes you completely dependent on the calculator. You really shouldn't use those constantly as you're doing all of your homework, because you lose a lot of your skills just from working off the top of your head. Okay, anyway, 5. How many 5s are in 6? 1. Okay, so if I take a 5 out of the 6, I get a remainder of 1, so I have 13 left. Let's see here, 5 into 13. How about 2? 5 times 2 is 10, so we have 12. I said we had 13 left, and I just said 5 and 2 is 10. So 13 minus 10 is 3. So our final answer is 12 and 3/5 Now don't forget we're talking about area, and so it's 12 3/5 square units. Got two more examples for you. Bam! If similar, these are the last two examples again. If similar, find the area of the larger hexagon. Six-sided polygon. Well, I was told they were similar, and they may be regular, but I wasn't told that they were regular, so I can't just look at this side of 3 and just automatically know that the area is going to be blankety blank. And I made up these areas, so I don't think they're actually regular. However, they are hexagons, okay? So this one has a side of 2 and this has a side of 3. I want, or I have the area, again, of the smaller hexagon, and I want to find the area of the larger one. Well, this is really just like the last example. It's even so much so that hopefully you can just pause the video right now and figure the answer out on your own. But, you know, let's just work through this. I have a side of 2, a side of 3. They are, again, similar. I want to find a multiple of change that's going to take this area for the smaller hexagon and find the area of the larger one. If I want to increase, obviously my area is going to get larger, so I need to make sure that I multiply by something that is larger than 1, which will increase the area. So I could do 2 over 3, which is fine. I could do that, and I could use that 2/3 ratio, but to make it easier, I'm going to do 3 over 2. So the areas, or the ratio of change for the lengths is the ratio of the sides is going to be 3 over 2. And that means that the ratio between the areas is going to be that 3 over 2 squared, which is going to be 9/4. So, if I know that this area is equal to 9 over 2, then this area is going to be 9 over 4 times larger. So it's just going to be, this area is 9 over 2 times 9 over 4, which is going to be 81 over 8. Now, let's see, can we reduce this? Of course, there's 1, 8, and 8, so that's going to be 1. So take that out, we have basically nothing left, so it's going to be, let's see here, 80, how about 10? 80 times 10 is 80, leaving with a remainder of 1, so it's going to be 10 and 1/8 square units. Same type of idea of dealing with, again, similar figures, looking at the sides, trying to work with the areas. A little bit more complicated on this one. The area of the large rectangle is 90. And then based on just that, we're going to find out what x and y are. Well, what am I going to do? 5 over x, 8 over y. I need to know what the ratio of change is between these two rectangles. And this 5 matches up with a variable, the 8 matches up with a variable, and this 90 doesn't match up with anything. So I kind of seem like I'm a little bit stuck, except I did say this was a rectangle, and we know how to find the area of a rectangle. The area of a rectangle is length times width. So the area of this smaller rectangle is not given, but because I know the length and width, I can find my own area. 8 times 5 is going to be equal to 40. So this area is 40 square units. So now what I'm going to be dealing with, this is my last example, and so I don't want to do the same type of example 4 times in a row. I'm giving you enough information to set up the ratio of change for the areas. Now remember, the ratio of change with similar figures, the ratio of change for the areas is A over B squared. So the ratio of change for the areas let's see here. Now again, do I want to do this as 90 over 40 or 40 over 90? I can work with both, but I need to find x and y of a larger rectangle. So again, I'm ultimately going to find a multiple of change, or a scalar multiple, to turn 8 into y and 5 into x. Well, I need to multiply by something bigger than 1 because I want to take these measurements from the smaller figure and increase their length for the larger one. So I'm going to do 90 over 40. both those values, you know, end with a 0, so it can be reduced. I can divide the top and bottom by 10. And get 9/4. So the ratio of change for the areas is 9/4. But don't forget from the first set of notes that that was equal to a squared over b squared. In other words, if I want some kind of ratio or proportion that's going to allow me to change my 8 into the length of y and use my length of 5 and find the length of x, I need a ratio of change or a proportion for the lengths. So I want to take that value and square root it. So the ratio for the sides is going to be the square root of 9/4. Now when you square root a fraction, all you got to do is square root the top, square root the bottom. So the square root of 9 is 3. The square root of 4 is equal to 2. And there's my multiple of change, 3/2. So if I want to find out what y is, that's going to be y is equal to its corresponding side of 8 times 3 over 2. Well, when you work with fractions, you really should make everything look like a fraction. So let me pop that 8 over 1. And we have 8 in the numerator and 2 in the denominator. So this will reduce. 8 and 2 are both divisible by 2. So divided by 2 is 1. And 8 divided by 2 is 4. So 4 times 3 is equal to 12. Yeah, I put some fractions in here, but I still need to be able to do these in my head. So we're getting back to whole number answers. And x is, well, we won't for this one, but it's 5 times 3 over 2. Well, again, let's put that 5 over 1 so we can see how the numerators and denominators again line up. And when we multiply fractions, we don't need common denominators. We just need to multiply the numerators and denominators together. So 5 times 3 is 15. And 1 times 2 is 2. 15 divided by 2, well, that's not a whole number answer, but 7 times 2 is 14. If I take 14 out of 15, I get a remainder of 1. So my final answer is 7 and 1/2. Now these are both just units, not square units, because they're no longer representing area, they're representing length. I'm Mr. True. Go do your homework.